Hi, welcome back to Ed Talks, the show where I spend 15 minutes researching a topic I know nothing about and then try my best to explain it back to you in as much detail as I actually can with what I learned briefly on the internet. Today's topic is going to be quantum teleportation. Now, quantum teleportation isn't actual teleportation. It's a really dumb name for it because you don't actually teleport anything physically. You teleport information. You teleport, and not just like information like in a book or like an email information, because we can already do that. There's nothing special about that. You teleport qubits, which are quantum bits, very similar to actual bits of ones and zeros, trues and false, but they're quantum. That makes them qubits. Really cool word to say too, qubits. Now, in order to send them, you have to establish a link between 2 points. You can't send something without a link. If you send a fax and there's nothing there to receive the fax, you didn't actually send a fax. So the 2 points you establish, you need to establish with your standard communication devices. So wires, radio lines, fiber optic cables, you want to use those to form a network to send your qubits through. Now a qubit itself, remember the quantum bits, very tiny because they're quantum, that makes things tiny, are particles. They're atoms. And that's what you're sending. You're sending the information stored in a particle or an atom as a whole. So when you send that information, you have the physical particle or atom in point A, and you send it to point B. Now what point B receives is an identical makeup from electrons, neutrons, photons, the electron shell, the inner shells, the outer shells, the whole atom. They receive an identical copy of it. But it's not really a copy because you moved the original one, all the information, over. So the information on the original one is gone and has been printed onto another one. In order to do that, you have to have blank atoms that can be imprinted on. So you send your atom from A to B. Your full atom with all your neutrons, electrons, photons, the electron shell, the correct atomic number, and everything you want in atom A, okay? And you want to send that exact information to atom B. So the people there can have all the information there without you having to call them or anything like that. This is used for various methods. We won't go into all the details of why this could be used for. Some simple ones are to send packets of information across great distances. Because information traveling this way can, in theory, travel at the speed of light, but never faster. So the way you get the information traveled depends on the speed of light, because you can't go faster than that, because light is the fastest thing in the known universe. So, A, B, proton, you send it over here to B. They receive it, they look at the data in it, and see if it's an exact match. One of 4 possible outcomes happen. Either it's sent exactly and you have a perfect quantum teleportation, which is yet to happen, or the information is sent near identical with variations, maybe either extra electrons, fewer electrons, electric protons, fewer protons, electric photons, or fewer photons. If you receive more or less of what you were supposed to have to begin with, you tweak the experiment, you tweak the system that you use to teleport the atom or the particle with, and you try again. You continue doing this as many times as necessary to finally get the exact proton with the correct levels and the correct numbers all moved. If you do that, then you've achieved quantum teleportation. This has yet to happen perfectly. We've had a few instances where we've transported the atom, but not the correct number of electrons or neutrons, and the longest distance we've ever transported one has been 100 and some odd kilometers. Kilometers, not a kilometer, a kilometer. It doesn't matter. A lot of miles. Now, the best way for this to be used is to send information from, say, here to space, or through space. If we ever colonize outside of our own planet, we can use this to teleport, because it's not really teleporting, because all you're doing is sending information. You're not sending actual physical objects. Again, like a fax. When you send a fax, you don't send the actual paper, you send the information on the paper, and it prints onto a new paper. Think of a particle as a piece of paper, okay? So a particle is a piece of paper. Now, you send all the information from one particle through your communications channel, be it wires, fiber optics, or whatnot, to another particle. And there it's printed back onto it. And that is quantum teleportation. Now, with that done, you can use it for various things. Okay? Remember back before we were talking about how you can use it to send information to and from space? Establishing your 2 points allows you to send massive amounts of information much quicker. Right now we have a hard time sending massive amounts of information to space. At least where it can be readily available, if you will. So, this process will help reduce cost and efficiency of moving information to and from large distances. Now, in order to establish your 2 links, because since we didn't cover that yet, we just said you needed 2 links, you have to have a quantum entanglement between the 2 protons that you want to be the same. So proton A, you need to entangle with proton B so that the information can be shared simultaneously. It's a very complex procedure that we're not going to get into today. It would cover more than an episode's length. And we don't want these to run too long, right? Remember what the great tool is, okay? There you go. Use it. Now, with entanglement done, you need a bell curve to get A and B linked up, to get the full effect, the full teleport effect linked up so there's no missing packets or missing information or extra information, because teleporting along, it might pick up extra qubits here and there, you know. It's not an exact science. It's very hard to teleport things long distances. Again, to teleport. So, teleporting data. A, B. With me? Okay. Now, that covers most of what quantum teleportation is. There's some more details that we could get into, and I'll try my best to explain them. I'm a little fuzzy on them. So we'll, the bell curve, the teleporting in different ways, or, one way with 2 different points. It's very complex in nature. You're talking about quantum physics, quantum entanglement, quantum teleportation. It's very complex in nature. But the simplest way to think of it is, again, a space fax. There we go. That's what we'll call it. We'll call it a space fax. And your qubits are your paper and your data. Okay? Now, sending your information from A to B requires power. A lot of power, because it requires a lot of power. You're teleporting things. You're moving particles on a subatomic level. And it's going to be identical on the other side, destroying the one here. Now, there's a caveat to this rule, because in quantum physics, qubits can't be erased or copied. So when you move it from A to B, it's not so much of a copy, because you're moving the actual proton itself, the actual atom itself, from here over here. But the one here, the shell is left behind. You have a shell remaining of it, a shell, right? This one, it takes all that information and goes from being an empty shell to being a full proton, or a full atom, or a full particle, if you will. So that covers the basics of what quantum teleportation is. Later on down the road, we'll come back to quantum physics or quantum entanglement even more, but that's a good starting point. With that, we'll wrap this episode up. I hope you have a great day. And if you want, leave a comment about what you think our next episode should be about. Have a fantastic day. Thanks for watching the Ed Talks. If you like this episode, be sure to like and subscribe to catch more. Also, check us out on social media, Facebook, Twitter, whatever platform you're on. And again, have a fantastic day.